Chapter 19. Let's put things in order. Sorting. In this chapter, you'll examine the topic of sorting data, putting data in some order. Alphabetization is the process of putting words in order. When you order numbers, you decide whether you want those numbers to increase in value, ascending order, or decrease in value, descending order. Next, you'll examine two specific examples of sorting algorithms. The selection sort, which relies on finding the minimum repeatedly, and the merge sort, which repeatedly halves the array. In this chapter, alphabetization and defined, ascending versus descending, the selection sort, finding the minimum, the merge sort. How data is arranged, sorting. When we arrange data in order, we sort it. It is important to be able to arrange a list of words in alphabetical order, or a list of numbers in increasing or decreasing order of value. If you had a list of lottery numbers, you would want to be able to arrange them so that you could easily look up a certain number in a list. There are many ways to sort data, and as you study the topic of programming, you will learn these different sorting methods. In this chapter, I will discuss the broad topic of sorting, and then study two particular sorts so that you can see how a sorting algorithm works. Think of each sort as a recipe for arranging data in order. Each sort has its own name, depending on the particular way data is arranged in order. The ability to sort is an important task when you are dealing with large quantities of data. The most obvious kind of arrangement of data would be the alphabetization of strings, putting words in alphabetical order. Names, strings, are alphabetized all the time. Look at this list of names that are not in alphabetical order. John, Nicola, Marie, Susan, Brian, Bridget, Margaret, Nick, Bernie, Al. If we alphabetize this list, we see that AI should be first, and then we see that Al should be first, and then we will examine the names that begin with B. After handling those names, we can look to the next letter in sequence, the J dot. Then we find that the names beginning with M should be placed before those beginning with N, and last we follow with the name Susan. Al, Bernie, Brian, Bridget, John, Margaret, Marie, Nick, Nicola, Susan. If you stop for a moment and analyze the work you did to alphabetize this list, you might not think it was much work at all. After all, you can see that Al is first because the name begins with an A. Next, you might admit that it required a little work to arrange the three names that began with B in order. You need to look at a second and third letters to see which name is first, second, and third among them. Now stop to consider how a machine with no intelligence would go about organizing data in some kind of order. Here we begin the topic of sorting, arranging data in order. First, I will introduce two kinds of order, ascending and descending. In the last chapter, we examined ascending order. We will be sorting data in ascending order in this chapter. Ascending versus descending order. Ascending order is the order we introduced in chapter 18 when we mentioned the requirement that a binary search can only be performed on an array that is in order. Ascending order means that the numbers in the array increase in value as you move through the array. For example, as you move from member 3 to member 4, you expect the value found at member 4 to be greater than that found at member 3. Look at this example of a list of numbers in ascending order. The numbers increase in value as you move from left to right. -8, -1, 2, 5, 12, 18, 19, 32, 41, 45. If an array were used to contain these values, the array's first holder slot would hold -8, and the second holder would contain -1, and so on. Descending order is just the opposite. Descending order is just the opposite. The values found at the front of the array on the left are bigger in value than those that follow on the right. Look at the same list of values which are in descending order: 45, 41, 32, 19, 18, 12, 5, 2, -1, -8. This list is in descending order because every value to the left is bigger than every value to the right. Now let's take this list and put the values into an array. Int list 10, list 0, 45, list 1, 41, and so on to list 9 being -8. As you move down through the list, the values become smaller. This array is in descending order. We will examine a few different sorts to see the basic method by which numbers are arranged in order. The selection sort. For a computer to sort organized data, it must follow a very specific set of instructions. There are different kinds of sorts depending on the method used. Each sort is named for the method it employs. The selection sort is a good sort to begin your study. As an analogy, let's start by looking at an example of a selection sort performed on a group of people at a party, and then we'll examine the sort applied to a list of numbers in an array. An analogy: the partygoers. Imagine a group of people attending a party. Someone not in the party plans to make a list of the youngest to oldest people in attendance. We will call this person the organizer. The organizer enters the room where the party is and asks the first person he meets how old he or she is. The organizer continues to ask every other person how old each is. One by one, he tries to find someone younger than the first person he asked. If he finds someone younger, he considers that person the youngest now. He continues to ask each person his age. When he finishes querying everyone, he retains the name of the person who was the youngest. The organizer asks that person to leave the room after he writes down the name first on his list. Returning to the room, he asks the remaining people, one at a time, their age. He will find the youngest person in that group and ask that individual to leave the room. He writes down the name of the person leaving. The organizer now holds a list of 2 people. The youngest person's name is at the top, and the next youngest person is listed second. The party is not as big as it was before, since 2 people have left. As the organizer pulls the remaining group to find the next youngest person, he writes down that person's name and asks him or her to leave. Now the party is missing 3 people, and thus is a smaller group. He now has a list of 3 people, the youngest, second youngest, and the third youngest of all the people that went to the party. The algorithm we are developing is to select the youngest in a group and put that person's name at the top of a list. Then we select the youngest person, really the second youngest, from the slightly smaller group the youngest is missing, since we asked her or him to leave, and follow the same procedure. Write down the name and ask the person to leave. The organizer keeps a list of each new youngest person found at the party, and also asks that individual to leave once he has written down the name. In this way, he can examine a smaller group each time to find the new youngest person. The list he keeps is growing. It is a list of the youngest through oldest people who attended the party. By repeatedly selecting the youngest person from the group, he is organizing the names of all the people who attended the party in order from youngest to oldest. 2 parts to the selection sort. The first part of the selection sort is to notice that we are selecting the youngest from a group and putting that person's name at the top. The second part of the sort is to recognize that we are examining a smaller and smaller group in each time. See Figure 19.1. Figure 19.1. The smallest number 2 of a group is shown outside the group at the top of a list. Then the group is shown without that member. Next, the smallest 5 is chosen from the group, and it is written second in the list. The third time, the smallest 10 is pulled from the group and written third in the list. This is how the selection sort works. Each sort you will study has some structure to its method. The selection sort selects the smallest number from a group and puts it at the top of a list. This number is removed from the group so that when you find the smallest in the remaining members of the group, you will be able to find the next smallest, and so on. Finding the minimum. Before we look at the selection sort performed on an array of numbers, we need to look at the part of the sort where we found the youngest person in the room. This requires some work. Finding the youngest person in a room is an analogy for finding the minimum in a list of numbers. The minimum is the smallest value in a list. When you find the minimum of a list, you are really finding the smallest value in a list of numbers. Let's examine this list of 6 numbers: 14, 32, 5, 12, 61, 7. As you look at the list, you can immediately see that 5 is the smallest number in the list. The task is more difficult for a computer. It has to be programmed to find this minimum. Let's look at what the computer might think in order to better understand how finding the minimum works. Computer, let's assume that 14 is the smallest number. Let's get the next number from the list, 32. Is 32 less than 14? No, so 14 is still the smallest. Good, less work for me. Computer, let's assume that 14 is the smallest number. Let's get the next number from the list, 5. Is 5 less than 14? Yes, I guess 5 is the smallest now. Computer, let's assume that 5 is the smallest number. Let's get the next number from the list, 12. Is 12 less than 5? No, so 5 is still the smallest. Computer, let's assume that 5 is the smallest number. Let's get the next number from the list, 61. Is 61 less than 5? No, 5 is still the smallest number. It has lasted longer than 14. Computer, let's assume that 5 is the smallest number. Let's get the next number from the list, 7. Is 7 less than 5? No, so 5 is the smallest value in the entire list. Let's do this exercise a second time, showing at least 2 replacements of the minimum value as you move through the following list: 21, 16, 25, 8, 19, 4, 1. Looking at this list, you can see that 1 is the smallest, but consider the work a computer would do if confronted by such a list, an array. Remember that the computer cannot see all the numbers in the list at once. Computer, let's assume that 21 is the smallest number. We'll get to the next number from the list, 16. Is 16 smaller than 21? Is 16 smaller than 21? 16 is now the smallest in the list. 21 didn't last for long. Computer. Let's assume that 16 is the smallest number. We'll get the next number from the list, 25. Is 25 less than 16? No, so 16 is still the minimum. Computer, let's assume that 16 is the smallest number. We'll get the next number from the list, an 8. Is 8 less than 16? Yes, so 8 will replace 16 as the new minimum. Fair enough. Computer, let's assume that 8 is the smallest number. We'll get the next number from the list, 19. Is 19 less than 8? No, 8 is still the minimum. Computer, let's assume that 8 is the smallest number. We'll get the next number from the list, 4. Is 4 less than 8? Yes, so 4 is the new minimum. The minimum has changed 3 times. Computer, Let's assume that 4 is the smallest number. We'll get the next number from the list a 1. Is 1 less than 4? Yes, so the minimum has changed again. After the computer has exhausted the list by examining all the members, the minimum of the entire list is the value that remains in the minimum holder variable at the end of the algorithm. When you program the computer to find the minimum, you first establish a value for a variable called minimum. Using the first value in the array is an efficient choice. Consider this fragment of code. Int collection 7. Collection 0 equals 21, collection 1 equals 16, collection 2 is equal to 25, collection 3 is equal to 8, collection 4 is equal to 19, collection 5 is equal to 4, collection 6 is equal to 1. Int minimum equals collection 0. The first value in the array is assumed to be the smallest since we have seen no other values. Now that the minimum has been assigned a value, the computer will need to look at all the other values in the array, one at a time, to make comparisons with the value in the minimum holder. If any better value is found, a lower value, then the minimum will need to be assigned that lower value. Look at this example of a statement that would cause the minimum to be replaced by a new lower value. If collection 3 is less than minimum, minimum equals collection 3. In the comparison between the values in collection 3 and minimum, the computer will evaluate whether it is true that collection 3 contains a value that is lower than the value contained in minimum. If the value of that relational expression is true, then minimum will be reassigned the value that is contained in collection 3. The old value in minimum will be replaced. Now look at all the work the computer does to find the minimum for this array of 7 members. Here are 6 statements that will look for a better minimum, a lower value than the minimum that is established initially with the value in the first slot of the array. If collection 1 is less than minimum, minimum equals collection 1. If collection 2 is less than minimum, minimum equals collection 2. If collection 3 is less than minimum, minimum equals collection 3. If collection 4 is less than minimum, minimum equals collection 4. If collection 5 is less than minimum, minimum equals collection 5. If collection 6 is less than minimum, minimum equals collection 6. This is how the computer finds the lowest value in the entire list. It methodically looks for a lower value in each of the slots of the array. The most important thing to notice, however, is that whenever the computer finds a lower value, it replaces the value in minimum immediately. You might have noticed that the preceding statements seem repetitive, and they are. We need to use a loop to save some time in our programming. Let's use a for loop to hit all the members of the array. For int x is equal to 0, x is less than 7, x equals x plus 1. Opening brace. If collection X is less than minimum, minimum equals collection X, closing brace. Now we are ready to see the entire block of code that allows the computer to find the minimum from an array of numbers. This block of code will work on any array. You only need to adjust the for loop so that it will spin the appropriate number of times. Minimum equals collection 0, setting the initial first value. For the minimum variable, for int x equals 0, x is less than 7, x equals x plus 1, opening brace. If collection x is less than minimum, minimum equals collection x, closing brace, cout. Cout. The smallest value in the array is minimum, period, end line. Remember the cout line. Remember the cout line can wrap to the next line. Note, remember to assign the value of the minimum variable, slot 0, the first member of the array. In order to find the minimum, the computer needs to constantly compare a new array slot with the most recent value in the minimum variable. It is possible for the value in the minimum variable to change several times before the for loop ends. On the CD, a program that shows the complete selection sort. Merge sort, a very fast sort. The next sort I will discuss is called a merge sort, which involves bringing together two halves of an array. The way it sorts numbers in order is quite different from the selection sort we just studied. For this reason, it is an interesting sort to study. Let's take a list of numbers from an array in order to see how a merge sort works on the list to organize it into ascending order. Numbers increasing as you move from left to right or from top to bottom. We will name each slot of this list underneath the number. 32 is 0, 12 1, 5 2, 18 3, 31 4, 4 5, 25 6, 7 7. How the merge sort works. Consider the array just presented. Initially, the array of 8 elements is viewed as one array. After the first halving, the 8-member array is viewed as two separate 4-member arrays. The next cut in each half produced 4 quarters. The next halving of each of those quarters produces the 8 individual elements. Consider how the array has been broken into halves repeatedly. See Figure 19.2. Figure 19.2. The array is shown broken in different places until each piece of the array is a single element. Now let's do this exercise again, but this time we will focus on the entire left half of the array, that is, the first 4 elements. We will ignore the right side of the array for now. 32, 12, 5, 18, 1 half, 31, 4, 25, 7, ignore this half for now. If we cut the left half in half, we will have 2 quarters on the left side. 32, 12, first quarter, 5, 18, second quarter, 31, 4, 25, 7, ignore this half. Each of the left two quarters is then cut in half. Now there are 4 individual elements on the left side of the array, while the right half is ignored. 32, 12, 5, 18, 4 individual elements. 31, 4, 25, 7, ignore this half. The left half of the array is ready to be reassembled or merged into the proper order. It is important to notice that as we reassemble the left half of the array, the right half of the array remains out of order. Merge sort is programmed to work on one half of the array at a time. Putting the array into order. Let's consider where we left off in the array. The first 4 elements need to be reassembled into the proper order. The first rule of merging is that you can only merge with the element that you most recently split from. What does that mean with our list? If you look back at the numbers 32 and 12 can be merged since they were split apart, but 12 and 5 cannot be merged because they did not come from the same quarter of the array. Likewise, 5 and 18 can be merged. Let's merge each of these pairs into the proper order. 32, 12 will become 12, 32. The 2 elements have been properly merged and are in order. Next, the 5 and the 18 can be merged. 5, 18 will become 5, 18. Now look at the left half of the array. It is still not in order, but it has undergone some ordering. Each quarter is in order. 12, 32, 5, 18. Now then, these 2 quarters of the array can be brought together, merged into a left half of the array. The 5 will be first, followed by the 12, then the 18 will be next, followed by the 32. 5, 12, 18, 32. Now the array, still undergoing the merge sort, looks like the following. 5, 12, 18, 32, left half in order. 31, 4, 25, 7. This half was ignored. Focusing on the right half. Let's do the same thing to the right half as was done to the left half of the array. We will ignore the left half for now. The right half, just like the left half, will be split into 2 quarters and then into 4 elements. 5, 12, 18, 32, ignore this half. 31, 4, 25, 7, the right half. If we cut the right half in half, we will have 2 quarters on the right side. 5, 12, 18, 32, ignore this half. 31, 4, 25, 7. 31, 4, third quarter. 25, 7, fourth quarter. 5, 12, 18, 32, ignore this half. 31, 4, 25, 7, 4 individual elements. The last 4 elements should now be reassembled or merged into the proper order. We need to remember that we can only merge with the element that you most recently split from. The numbers 31 and 4 will be merged since they were split apart in an earlier step. The numbers 25 and 7 can be merged. Let's merge each of these pairs into the proper order. 31 and 4 will become 4 and 31. The two elements have been properly merged and are in order. Next, the 25 and 7 can be merged. 25 and 7 will become 7 and 25. Now look at the right half of the array. It is still not in order, but it has undergone some ordering. 4, 31, 7, 25. Now these two quarters of the array can be brought together, merged into unordered right half of the array. The 4 will become first, followed by the 7, then the 25 will be next, followed by the 31. 4, 7, 25, 31. Now the array has two halves, a left half and a right half, that are ready for a final merge. Each half looks like the following. 5, 12, 18, 32, left half in order. 4, 7, 25, 31, right half in order. The final step of merge sort is to merge these two ordered halves. The result of this merging is an array in ascending order. See figure 19.3. Figure 19.3. The array is shown as the merging of these two ordered halves. Each member from each half goes into its proper position. The merge sort works by a process that allows an array to be cut into halves repeatedly until individual elements are left. Then those members are brought together, each half with its other half, into the correct order. Eventually, the entire array is in order. The programming code to execute the merge sort involves a process called recursion, which we will study in the next chapter. Summary. Sorting means arranging data in order. Arranging a list of names in alphabetical order is an example of sorting. Sorting a list of numbers means arranging them in ascending or descending order. Ascending order arranges smaller numbers before larger numbers in an array. Descending order puts numbers that are greater in size first, followed by smaller numbers. Next, we covered the selection sort, which relies on the ability to find the minimum in a list. The selection sort was explained through an analogy of people attending a party. Then we looked at the selection sort applied to a list of numbers. Next, we defined the minimum of a list. It is the smallest number in a list. In order to find the smallest number, the first number from the array, slot 0, is assigned to a variable called minimum. Then the algorithm works by looking at the rest of the numbers in the list, one at a time, through the use of a loop. As you look at each number, you test whether that number is smaller than the number that is presently assigned to the minimum variable. When the loop is done spinning, the value in the minimum variable is the smallest number in the list. The merge sort was the second sort we examined. It works very differently from the selection sort. The merge sort repeatedly cuts an array into halves until there are only single elements of the array. Then those members of the array are assembled into their proper order, 2 pieces at a time. The sort gets its name from the merging that occurs as the pieces are put back together properly.